Hey everybody, and welcome back to Algebra 2 Online. So my last video went a little bit long, so this is just kind of a quick end to the last video where I introduced the unit circle. I just wanted to say a little bit about how sine, cosine, and tangent actually work, because they're kind of weird functions actually if you think about them. They are functions, and just like functions have inputs and outputs, these do too. But the inputs for all of these are angles, okay, which is kind of odd. But you plug in angles, okay, and you output a ratio of sides in like the triangle, right, that we've been using. So it's kind of an odd thing, and since it is kind of weird, it's what we actually call a transcendental function. There's some other ones in the world like this too. The idea is that they basically transcend the niceties of algebra. It's not very normal to plug in angles and get out ratios of sides. It's kind of a weird thing. You still are plugging in a number and getting out a number, but what the number is kind of an odd thing if you think about it. So the notation for this too is that we do always write sine, cosine, or tangent operating on the angle. So it is a sin to write sin, is what I always like to tell students. It's kind of like writing log without anything. Like if you just write log and that's it, it means nothing. But as soon as I do log of 100, then it's going to equal 2, right? Because now I can say, I'm thinking of it as base 10 squared is 100, right? So you take the sine, the cosine, the tangent, whatever, of an angle, and you get out a number that is a ratio of the sides in a right triangle. So that is what they are doing, okay? And what you're going to have to do with them is basically you're going to be looking at the ratio in special triangles entirely in the beginning here. So we have all sorts of special triangles, just highlighting a few of them here. But all of these ones, we'll just do one more, do one right here. All of these are right triangles, and you always draw it so the right angle is down on the x-axis. This one is a 45, 90. This is a 60 degree, whereas up here it's 30. And then this blue one, this is 30, and this is 60, okay? And turns out that you really can just do all unit circle problems if you know the sine, cosine, tangent of these ones in the first quadrant. Because what you can do is you can basically, as long as you can calculate the sine, cosine, tangent in this quadrant, you just use the all students take calc trick, and you can get the sine, cosine, tangent in any quadrant, because you can just think about like flipping it, mirroring the triangle over. So what I mean by that is like, okay, here's a unit circle, let's say. Here is this 45, 90, like this one right here. The idea is like you can kind of flip it into this quadrant, and there's a lot of symmetry I'm trying to draw. Those are congruent triangles right there, okay? But the idea is like the sine, which is the y-coordinate, right? It's the same y-coordinate in both quadrants, which is why it's going to be the same in both quadrants there, right? And you can do this for the cosine too. The cosine, this x, that distance is the same this way, but this is negative, which is why if you can get the cosine in this quadrant, you can just use it for this angle as well, but you just know that it has to be negative because sine's the only one that's positive here. And there is a great trick that is in another video that I did not make, but it's a really nice trick that I want you to use to do these kinds of things. And if you've seen my room, I have a poster that says square root of fingers over 2 and square root of fingers over square root of fingers. And that is related to the trick. So I will talk about it in class, but it's an insanely useful trick that to this day I still use. I learned it when I was in high school and literally never forget it, and I use it almost every single day. So we will talk about that in class, but there is going to be another video that kind of shows you how you can find the sine, cosine, tangent of any of these, and then it's really useful because you can just mirror it to other quadrants to get the sine, cosine, tangent in the other quadrants. So very, very handy little trick. One more little problem I just want to do. So I just haven't done one like this, and I think it's good to kind of see this kind of problem. So the terminal side of an angle in standard position, so one starting here, contains the point at -3, -4. So -1, 2, 3, -1, 2, 3, 4 is right there. So basically there's an angle that terminates right there, right? I want to find the exact values of sine, cosine, and tangent for such an angle. So if you just think of triangles, it's really not too bad. So this is kind of the triangle you can think of, right? And we have that this is -3. We have that this is -4, right? So if we want, here it's not necessarily a unit circle, right? But we can get that by just doing Pythagorean Theorem. So -3 squared plus -4 squared equals like my question mark squared, right? So 9 plus 16 equals question mark squared. That's 25, question mark squared. So my hypotenuse is going to be 5, right? And from that point, I can do sine, cosine, tangent. Sine of that angle is just going to be the opposite, -4 over the 5. The cosine of the angle is the adjacent, -3 over 5. And the tangent, right, is the opposite over the adjacent, so -4 over -3 or 4 over 3. And remember that all fits nicely with the all students take calc thing. Tangent should have been positive, but none of the other ones should be positive. And so yeah, so that's basically just how you could get the exact values of sine, cosine, tangent, even though you don't know the angles. There was no mention about the angle, purely just mention about where the angle ends, like the point that it ended at. And then I could still use what I've learned about triangles and trig and things to get there.